Okay, so very good morning to everyone. Yeah, firstly, I want to thank you guys for attending this course. Yeah, it is a 5-day course. In the first part, actually, yeah, especially the first lecture is more like a refresh of the past knowledge we have learned. So I will introduce the basic concepts and compile the difference between the different design. And after that, starting from the second class, I will more focus on the new knowledge and especially some the findings we have obtained from the research, either by our group or by other other groups. Okay, so in the first part, I'm going to introduce the basic design and major emissions of various internal combustion engines. Firstly, I want to introduce the history of heat engines. Basically, the heat engines is the device which transforms chemical energy from a fuel into thermal energy, then utilize system energy to perform useful work. Um, as a result, the thermal energy is converted into mechanical power in the heat engines. So this kind of device we call the heat engines. The earliest heat engines actually are steam engines, which triggered the first industrial revolution, correct? Especially in the UK. Okay, since then, actually the internal combustion engines was proposed, especially in 1867. Otto proposed the first internal combustion engines. This engine is a free piston engines with an efficiency of about 11%. Okay, so as we know, the efficiency is very low. Because we know the modern engines, like gas engines, the efficiency can be as high as 40%, especially for the direct gasoline injection engines, correct? Even the normal gas engines, the efficiency is about 30%, and diesel engines is much higher, can achieve more than 50% for the big engines for marine engines. Okay, so in 1876, Otto modifies the four-stroke free piston engine into a gasoline engine. So this engine is the basis of modern S engines. Then in 1892, Rudolf Diesel proposed a new internal combustion engine. Yeah, it is a diesel engines. So this one is the basic history for the internal combustion engines, especially for gas engines and diesel engines. Now I'm going to introduce the basic classification of heat engines. In this part, actually, we're going to show you the 8 major heat engines. At first, actually, heat engines can be divided into internal combustion engines and external combustion engines. Internal combustion engines we are very familiar. For example, gas engines, diesel engines, and also the jet engines also belongs to internal combustion engines. Yeah, but external combustion engines maybe not so familiar because all our students come from the maybe from the internal combustion era instead of external combustion engine era, but it is still important for us to understand the difference, correct? So in this part, I'm going to show you how the 8 different engines are designed. Okay, so first of all, I want to introduce the internal combustion engines and the external combustion engines difference. Okay, so let me show you the 2 designs. Okay, the first one is the open cycle gas turbine engines. It is also a jet engines. The second one is closed cycle turbine engines. It is actually it is a external combustion engines. Okay, later we'll share with you guys about the difference between these two. So for the internal combustion engines, especially the engines, here show you the schematic. Yeah, so the schematic is quite simple. So you can see the major components is in panel. This one is compressor. This one is a centrifugal compressor. The second major component is the combustion chamber. And the last one is a turbine. And also we have a nozzle. Okay, this nozzle achieves to increase flow velocity, and thereby we can produce a uh, a big thrust. Thereby we can push the airplane to move forward. Okay, so let me show you a video so that you can better understand how the engine are designed and the basic working principle. So let me show you the video first. Okay, so here we show you how the engines are designed, the major components, and the function for each component. So let me explain some of the concepts maybe. Okay, so here shows the basic structure. We can see there are some major components. The first one is a big frame. Okay, this big frame actually is designed to draw as much as possible fresh air, because we know the jet engines should be produce sufficient power, and thereby we can push the aeroplane to move forward, correct? So the engine should be able to draw as much as possible fresh air. Then we can produce more power. That's why a B5 is a descent in the jet engines. And the second one, okay, this one is a gap beam. Okay, this one is a gap beam. Actually, from the video, we can see this gap beam is stationary, which means that this gap beam is not rotate, correct? So what is the function? Why we design such a gap beam? What is the function? Anyone knows? Yeah, if you have any comments, you can switch on your you can mute your mic and speak. Okay. Anyone knows the function of this gap bin? Why we design such a gap bin? This can be stationary. It's not moving. Correct. Okay, yeah, this gap bin actually is used to change the flow direction. So that the fresh air can enter the multi-stage compressor from the along the exit direction. Okay, thereby we can easily enter the multi-stage compressor. So the major components this multi-stage compressor. From the first part, actually we can know in the high sky, the temperature is quite low, can be negative, correct? Can be minus 30 degrees C, minus 40 degrees C. After flow through this multi-stage compressor, then the pressure will be increased and the temperature also will be increased to about 450 degrees C. Okay, with this high temperature, then the combustion process can be self-sustainable. Otherwise, you have to ignite, repeat the ignition process. Okay. Okay, so this is a multi-stage. Yeah, it's used to increase the pressure, increase the temperature of the fresh air, so that we can sustain the combustion process. And okay, this multi-stage uh, compressor actually has some other functions. For example, increase the power produced by the jet engines, and increase the power, because we know the aeroplane need a lot of power and thrust, okay, to push the aeroplane to move forward, correct? So the fourth one is a combustion chamber. Okay, this one, okay, this one is a combustion chamber. So in basically the fuel jet fuel will be injected into this combustion chamber and burnt inside. Thereby increase temperature of the combustion products significantly. Okay, and for example, from 450 degrees C to more than 1,700 degrees C. Then the high temperature, high pressure gas will flow through this turbine. So in this process, part of the thermal energy will be converted into mechanical power, correct? Thereby we can use this mechanical power to drive this big frame, to drive this multi-stage compressor. Okay, and also we can also collect with the electricity generator, okay, produce electricity. Thereby we can supply electric power to the aeroplane, for the lighting system, for the air conditioning system, and so on, correct? Okay, then the last part actually is a nozzle. We can say actually in this design, in this part, actually the diameter is the biggest one, and from this position to the exit, we can see see the diameter will decrease. Okay, so by this design, actually we can create a nozzle shape. By using the nozzle shape, we know the function of nozzle is to increase the flow speed, correct? So in this process, actually can convert the thermal energy into kinetic energy and increase velocity, correct? Thereby we can produce a greater thrust and for the aeroplane application, correct? So this one is the basic design and the major components. Okay, actually you can you can see some other very special designs. For example, in this jet engine design, actually only 20% of fresh charge will flow or fresh air will flow through this core parts, flow through this multi-stage compressor, combustion chamber, and the turbine. And the 80%, the other 80% actually flow through by this position, flow through this flow path. Okay, so why we design the jet engine like this with 80% bypass and only 20% supplied to the jet engines are used for the burning of jet fuel. Okay, so anyone knows the reasons why design like this? Okay, so you can see here, about 80% will bypass, okay, actually don't attend the combustion process, and only 20%, okay, will flow through this multi-stage compressor, combustion chamber, and turbine, and participate the combustion process, correct? So why design the jet engines, yeah, with 80% bypass instead of use the air to produce more power? Okay, anyone else? Please feel free to give any comments. Okay. Okay, actually, this kind of design is very useful. Firstly, this design actually can cool the jet engines. Just like I mentioned, in the in the core part of the jet engines, the peak temperature can be as high as 1,700 degrees C, correct? So under such high temperature conditions, actually this engine can be easily burned. Okay, can be easily burned. So by design, this engine shows that 80% of fresh air can flow through the surrounding area, can flow through the position. So this fresh air actually has no temperature, correct? So can help to cool down the casing of this jet engines. Okay, so by this way, we can cool down the jet engines, okay, thereby protect the jet engines. So that is jet engines can maintain its structure, correct? Can maintain its structure. Okay, so this way is designed for the reliability of the jet engines. Okay, secondly, actually you can see when 80% fresh air flow through this flow path, and this flow path also are designed as a nozzle, correct? So you can see from here, inlet to the outlet, you can see the flow path actually decrease, which means that this design is convergent nozzle. So by this way again, we increase velocity, and at the same time, because this fresh air will absorb heat energy from the jet engines, correct? And further increase the temperature. So by this way, we can significantly increase the pressure, increase the flow speed, okay, thereby produce a greater thrust for the jet engines. Okay, so this one also basic design and operating principle for jet engines. Okay, let's go back to the go back to the slides. Okay, so we have introduced how the open cycle gas turbine works. Okay, the next one is a closed cycle turbine engines. So this one actually is commonly used for the power generation, the power plant, correct? So the basic design actually is quite simple. We have a furnace. Okay, this one is a furnace. the fuel will be burnt in the furnace and release heat energy, correct? Then also has a this flow passage, okay, this one. So water will flow through this heat exchanger, and in the furnace, okay, the heat energy will be transferred from the combustion products to the water, and then converts water into steam. And then we use the high pressure, high temperature steam to drive the steam turbine. Okay, thereby, okay, in this process, the thermal energy will be converted into mechanical power, correct? Then again, the steam turbine is connect with the electricity generator. Okay, thereby we can further convert the mechanical power into electricity. So in this design, as you can see, the water will flow through the heat exchangers, become steam, then flow through the steam turbine. The pressure, temperature drop, then will be condensed to form water, right? So in this design, we can see actually the working media is water or steam, and this steam actually recycled in this system. So the steam actually is not discharged from the power plant, correct? It is recycled. That's why we call this operating cycle as closed cycle. Okay, as closed cycle turbine engines. Okay, this one is commonly used for the power plant. Okay, used for the power plant. So now we can see the difference between the internal combustion engines and the external combustion engines. First one, so in this design, we can see the working media. Okay, the working media is the combustion products, correct? So in this process, okay, in the internal combustion engines, we can see the working media participates the combustion process, correct? However, in this case, we can see the combustion products actually is burnt in the fuel is burnt in this furnace, and this the combustion products after transferring gets the heat to the water to the steam, then the exhaust gas will be discharged from here. So we can see in this case, the working media is a steam, it's not the combustion products, right? So in this case, the working media does not participate the combustion process, correct? So this one is the first major difference between internal combustion engines and the external combustion engines. In the internal combustion engines, the working media participates the combustion process. However, in EC engines, the working media does not attend the combustion process. Okay, so this one is the first major difference. Okay, in S engines, working media participates combustion process. EC engines, working media does not participate the combustion process. Okay, so second major difference, in the external combustion engines, we can see, okay, this one is a heat exchanger. Okay, this one is a heat exchanger. However, in the internal combustion engines, we don't have heat exchanger, correct? Okay, so this one is the second major difference. And the major difference is that, okay, the power density produced by S engines is much higher than the external combustion engines. Okay, so we have the S engines has higher power density and the E engines has a lower power density. And the last one, for the jet engines, basically only liquid fuel or gas fuel can be burned. However, in the E engines, any types of fuel can be burned. For example, we can use rubbish, we can use coal, we can use solid waste, correct? We can use all kinds of fuel. We can use liquid fuel, petroleum. We can use gasoline. We can use diesel fuel, and also can use gas fuel, for example, natural gas. Okay, so any types of fuel can be used for external combustion engines. Okay, so here we will show you the major difference between IC engines and the EC engines. Okay, so far, any questions? If no questions, we'll move on. Okay, so next one I want to introduce is the difference between the reciprocating engines and the rotary engines. Since rotary engines still used in one of the car manufacturers. Okay, I'm not sure whether you guys know which company is still uses a rotary engine design for the car. Okay, it's a Japanese company, Mazda. Okay, now let me introduce the major difference between the reciprocating engines and rotary engines. So this one we can see this is the right one. We show you the rotary engines, the basic operating principle. So actually there are only two major components. One is the rotor, correct? The inner one. The second one is the casing, correct? So you can see the rotary engines actually the working process consists of four process, namely intake process, compression process, ignition process, and the exhaust process, correct? And also can see for the rotary engines, the fresh charge was delivered to the engine continuously here, correct? So can see the fresh charge is delivered to the engine continuously, correct? Okay, now let me show you how the reciprocating engine works. This one is very simple. Okay, so now we can see how the reciprocating engine works, correct? So compares two designs. Yeah, if we compare two designs, you can see for this kind of engine, the fresh charge is delivered to the engines continuously. And in this design, actually only in the intake stroke, correct? We have fresh charge supplied to the engine only as a first stroke. Okay, this one is the intake stroke, correct? So fresh charge will be drawn into the engine, correct? Okay, so compare these two designs theoretically, rotary engines is able to produce more power, correct? Because in this design, the fresh charge is delivered to the engine continuously, which means more energy will be produced, more fuel will be burned in the rotary engines, and more power will be produced, correct? This one is the theoretical results, correct? However, this kind of design also has some shortcoming or disadvantage. Okay, firstly, the sealing actually is a major challenge faced by the rotary engines because we know we can say actually the sealing between the different process, different chamber actually is by the tip of the rotor and the casing, correct? Okay, and so this kind of sealing actually is always face some problems. Okay, you cannot fully seal, you cannot fully isolate the contact between the different chamber. Okay, so which means there's some kind of a leakage, some kind of leakage. Okay, as a result, rotary engines basically the compression ratio usually cannot be too high, because the sealing is a major problem. Okay, and the efficiency, also this kind of engines, the efficiency actually is lower than the four-stroke engines, than four-stroke engines. So this is also a major difference between these two designs. Okay, the next one I want to introduce is four-stroke engines and two-stroke engines. Four-stroke engines, just I have shown you already. Okay, the basic working process, correct? So one cycle for four-stroke engines, one cycle consists of four strokes, namely intake stroke, compression stroke, power stroke, and exhaust stroke, which means the piston will be moving between TDC and BDC for 4 times. Okay, for 4 times to complete one cycle. However, okay, for the two-stroke engines, actually to complete one cycle, the piston only moved for 2 times between TDC and BDC. This animation actually shows you the basic, okay, the most simplest design for two-stroke engines. I want to show you another video for two-stroke engines so that you can better understand the basic design and operating principle for two-stroke engines. So let me show you another video. Okay, so here we show you the two-stroke engine works. So the design actually quite simple. So this one we can see the piston actually has 3 different functions. The first one can function as a exhaust valve. So you can see when the piston move down and uncover the exhaust port, correct? So we can see the exhaust gas will be discharged from the cylinder, correct? So the first function of the piston actually is a function as a exhaust valve and can control the opening and the close of the exhaust port. Second function actually acts as a intake valve. So we can see as this is a piston move down, then the transport port will be open. Okay, so you can see when the piston move further down, then the transport port or the inlet port will be opened and the fresh charge will be delivered to the cylinder. And the fresh charge will swash, okay, the exhaust gas and push the exhaust gas to move out, correct? And actually, such a third function, okay, this piston also can function as a compressor or pump. How works? Okay, so this piston also has another function, can act as a pump or compressor. So how this function works? So we can see actually when this piston move down, in the casing, okay, in this casing, we can see the body will decrease because the piston move down, then the piston will occupy space, correct? As a result, in the casing, okay, this is a crankshaft casing, then the body will decrease, correct? So which means the gas in the casing will be compressed, Okay, thereby increase the pressure, the density of the fresh charge in this casing, right? Thereby, when this transport port or inlet port is open, okay, then the higher pressure and higher density fresh charge will be delivered into the cylinder, okay, into the cylinder, okay. So in this case, as you can see, the piston has three functions. First one can act as a exhaust valve, can control the opening and close of the exhaust ports. Second one can function as the inlet valve, can control the opening and close of the intake ports. And the third one can act as a pump or compressor, correct? Okay, however, compact, okay, this two-stroke engines actually can produce a 1 power stroke every revolution or every turn. So in theory, compared with four-stroke engines, okay, these two-stroke engines can produce double power, correct? Since there's 1 power stroke in one revolution in two-stroke engines, and however, in four-stroke engines, every 2 revolutions, there's only 1 power stroke, correct? So in theory, two-stroke engines is able to produce a double power compared with four-stroke engines. Okay, that's why for marine transportation, usually the two-stroke engines is employed for the ship for marine transportation, and also for the motorcycle. Basically, two-stroke engines is employed because theoretically, okay, this kind of engine is able to produce double power. For motorcycle application, as we know, the space for installing the engine is very limited, correct? So the greater the power density, the better, correct? The more powerful. That's why for the motorcycle, actually two-stroke engines is better than four-stroke engines. Okay, so is there any shortcoming with two-stroke engines? Correct? Yeah, actually two-stroke engines basically has lower efficiency than four-stroke engines. Okay, why? Actually, from here we can see, for this kind of two-stroke engines, we can see, actually that's a duration. Both the inlet valve and the exhaust valve are open, which means part of the fresh charge can be discharged from here directly before attending the working process, correct? So the part of the fresh charge will be leaked or will be discharged directly from the exhaust ports, okay, thereby bring down the efficiency, correct? Okay, so this one is the first reason why two-stroke engines has more efficiency than four-stroke engines. Secondly, actually you can see in the two-stroke engines, the exhaust port is open in the middle of the cylinder wall, correct? Which means the power stroke is not a full stroke, correct? It is not a full stroke, correct? Because the exhaust port is open in the middle of the cylinder wall. Okay, once this exhaust port is open, then the pressure will drop immediately, correct? As a result, the power produced by this engine will decrease, okay? So because of these two reasons, and the overall power, overall efficiency of two-stroke engines will be lower than four-stroke engines. Since two-stroke engines is simpler in terms of structure, yeah, because we don't have intake valve, we don't have exhaust valve. Also, we don't have a control system, correct? So it's very simple. In terms of design, it's very simple. However, the efficiency actually is lower than four-stroke engines. Okay, so here's a summary on the difference between the four-stroke engines and two-stroke engines. So for four-stroke engines, we have inlet and exhaust valve, and the two-stroke engines, we don't have valves, correct? And the four-stroke engines is more complicated and heavier, and the two-stroke engines are simple and light. For four-stroke engines, there's only one power stroke every 2 revolutions, but for two-stroke engines, there's one power stroke every 1 revolution. Four-stroke engines basically has high efficiency, and the two-stroke engines has low efficiency. And also for four-stroke engines, the lubrication oil consumption is lesser than the two-stroke engines, because for two-stroke engines, actually the lubrication oil is directly blended with the fuel. Okay, the lubrication oil is directly blended with the fuel. Basically about 2%, 3% lubrication oil will be premixed with the fuel. And four-stroke engines is a less uniform torque because there's only one power stroke every 2 revolutions. Okay, so less uniform. However, for two-stroke engines, there's one power stroke every revolution. Okay, so it's a more uniform torque. Okay, so next one I want to introduce the major difference between the four-stroke gas engines and the four-stroke diesel engines. Okay, so here we show you how the four-stroke engines works. So you can see four-stroke engines, the intake stroke, in the intake stroke we can see only, okay, the fuel admixture will be drawn into the engine, correct? And however, for the diesel engines, only fresh air will be drawn into the engines. Okay, second stroke is the same. It's the same compression stroke. There's no difference. Then, okay, in the power stroke, we can see the combustion process was initiated by the spark. Okay, by the spark. However, for the diesel engines, the combustion process is ignited by compression. Okay, by compression, it is auto ignited by the high compression ratio. Okay, the rise actually quite similar. Okay, so four-stroke is also the same. And okay, so for the diesel engines, the fuel is injected into the engine directly from the high pressure fuel injectors, correct? But for gas engines, the fuel is premixed with the air and then supplied to the engine through the intake manifold, correct? So this is the difference between the four-stroke gas engines and the four-stroke diesel engines. And also here we show you the previous diagram for Otto cycle and diesel cycle. So if we compare the heat addition process or combustion process, so for gas engines, combustion process is more like a constant volume process from point 3 to point 4. Then for the diesel cycle, combustion process occurs from point B to point C. So this process is more like a constant pressure process. Of course, this is theoretically, okay? So here we show the major difference between four-stroke engines, four-stroke gas engines, and four-stroke diesel engines. First one, the ignition method is different. Gas engines is ignited by spark ignition. Diesel engines is compression ignition. For gas engines, fuel is introduced into the intake manifold and premixed with the fresh air. But for diesel engine, fuel is directly injected into the combustion chamber by the end of compression stroke. And so the major difference is the compression ratio. Basically, gas engines has lower compression ratio. It is from 6 to 10. However, this engine has higher compression ratio from 16 to more than 20. Gas engines basically has no efficiency. It is only about 30%. These engines has a high efficiency, usually it's 45%. But for marine engines, for the low-speed engines, actually the efficiency can as high as 53%. Okay. And so next one is a gas engine, so it's lighter. And these engines are heavier and sturdier. Okay, so one question for you guys. Why gas engines is lighter than diesel engines? Okay, so this kind of questions can appear in the final examination for this module because by the end of this course, actually we have examination. Okay, so yeah, usually if I hand that during the lectures, during the class, then you can pay more attention to this kind of question. Okay. For gas engines is lighter than diesel engines because this one, gas engines has lower compression ratio, which means that the peak pressure will be much lower than that for diesel engines. That's why the design of gas engines is lighter, lesser steadier, less steadier, correct? Okay, for gas engines, combustion process is more like similar to constant volume process. In the actual combustion process, of course, it's not constant volume, but we can use a constant volume combustion process to represent gas engines. For diesel engines, it's constant pressure combustion process. And the gas engines basically produce more CO and HC emissions. And these engines produce more NOx emission and soot emissions. Okay, so again, one question is why gas engines produce more CO and HC emissions, and these engines produce more NOx and soot emissions. Okay, gas engines usually is working at higher fuel air ratio conditions. Okay, so fuel air ratio can be usually from 0.7 up to 1.05. Correct? The fuel air ratio is higher. Okay, it's higher than that for diesel engines. That's why gas engines tend to produce more CO and HC because the fuel air ratio is very high. High for diesel engines, gas fuel air ratio is much lower than that for gas engines. Okay, usually it's from 0.5 to 0.9. Okay, so these engines can produce lesser CO and HC emissions. And these engines tend to produce more NOx emission and soot emissions. These engines produce more NOx emission because the higher pressure compression ratio, higher temperature, higher pressure. Okay, as we know, NOx emission actually is a high temperature products, correct? And soot emissions, because for these engines, the fuel is injected into the engines, they choose a high pressure fuel injector, right? And the fuel, okay, so the fuel distribution is not uniform. Some regions, the fuel ratio can be greater than 1, but in some region, the fuel ratio is very lean. Okay, so in the region with rich fuel ratio conditions, then tend to produce more emissions, correct? Okay, the last one, I think we can, it's time already, so we'll move this one to the next class, okay? So we'll stop here, we have 10 minutes break.